Because if I'd started the video and the sound, it would work better, you think?
Yeah.
Yeah, I hate Zoom, but that's okay. It's kind of cool.
Was it you saying the slide? It's better.
So are we good, Nigel?
Yep.
Okay. All right, welcome. Obviously, I'm not Pam Ishmael. I'm Dan Gallagher. I'm a professor in the Department of Food Science and Nutrition, if we haven't met before. I teach on the nutrition side of the world. And why Pam asked me to come and talk to you today about vitamin analysis is because I teach the graduate level nutrition course, vitamin and mineral biochemistry. So while we don't really talk much about vitamin analysis in that course, I obviously over 30 years of teaching the course, you pick up a few things, including some things about that. So that's the plan. This will be, the recording will be uploaded to Canvas, and I will also distribute this copy of the slides, because as I said, Dr. Ishmael gave me a set of slides and I tweaked them a little bit to make them throw in a few fun facts. So that's where it is. Any questions before we get started? We're all good? Okay, so I do this in my vitamin and mineral biochemistry course. I start off saying, what is the definition of a vitamin? So if your grandmother came up to you, so this is going to be a layperson. If your grandmother came up to you and said, what is a vitamin anyway? How would you answer that person in a way that she could understand? Not some biochemical definition, but the way your grandmother could understand. What's a vitamin? Yes.
It's an organic molecule that shows up in very small quantities in food and helps us, helps our bodies regulate various things. This has various functions.
Okay, so your grandmother would understand organic molecule, right? Because she's a biochemist by training.
I don't think you need to be a biochemist
to know what organic means. You don't think so? Okay, yes.
Say it's substance in food that we're not seeing that are helping our body to work properly, so that our body can function in what we like normal conditions of living.
Okay, fair enough. So I didn't catch it. Did you say that our bodies need it? Is that what you said? Okay, and did you say it was in food? Okay, she said that was in food. Is that true? All the time? That we need it in when you said it's in the food and we need it, I implied that we need it in our food. And that's the only way we can get it. Is that true? You think?
Yeah, supplements.
Say that again.
Yeah, we can synthesize in our body some vitamins.
Okay, which ones?
Like vitamin D, yeah.
Vitamin D. Okay, that's great. That's absolutely true. So can we synthesize it now, by the way? Not a chance. We stopped in October. So if it was sunny today, which is not, but if you were to go out in the parking lot on a sunny day in this time of year, and don't do this, leave this for the professionals. But if you were to take all your clothes off and stand there in the parking lot with the sun on you, you would make exactly 0 vitamin D. Okay. So if you want to know why, you'll have to take my vitamin and mineral biochemistry course. So are there any other vitamins like vitamin D where we don't absolutely have to have them in the diet?
Okay.
No, we need vitamin K in the diet. It's a myth. You might be referring to this myth that we can make it in our large intestine from fermentation of bacteria there, or maybe not, but that is a myth that's going around. It's not true, but you'll even read that in semi-authoritative areas. So it's not true, don't believe it. Okay, but there is one more, yes. Vitamin E. We need vitamin E. Yeah, that's not one of them. I'll give you a hint. It's not a fat soluble vitamin. That narrows it down. Okay, you're raising your hand tentatively.
Vitamin C.
Vitamin C. If you're a guinea pig and us, we need it. But if you are a horse or most other kinds of mammals, You don't need it because you can make it, but we absolutely need it. Okay. So I'm going to tell you, because I don't want to spend half the class doing this, it is the vitamin we call niacin. Niacin. And the reason is we have a limited capacity. You guys see, this is worth the cost of showing up today to know this. Okay, just that little tidbit. Niacin can be made from the amino acid tryptophan. If you get enough protein in your diet that contains an ample source of tryptophan, we actually can make enough to meet our requirement. So these vitamins, vitamin D, tryptophan, or excuse me, niacin made from tryptophan, they're referred to as conditionally required. Conditionally required. Okay. So why do you think it's important to analyze the vitamins in food? Yes.
Nutrition labels.
Okay, good enough. And why do we have nutrition labels?
So that we know it's food.
So that we know what's in there. And why would we care what's in there? Yes.
Make sure we're getting the amount of whatever it is that the body needs.
To make sure we're getting enough. Because if we don't get enough, and this happens, it's happened a lot through history. It has killed vitamin deficiencies. I'll tell you now, have killed millions of people over the history of the human race. So we want to know how much is there, so we make sure we're getting enough, and that you're able to function optimally in terms of that, what that particular vitamin does. Okay, so here's a common, little more formal definition. It is organic, as you said. That's absolutely true. And it says cannot be synthesized in sufficient quantities, and that's where the conditional requirement can come in. We can get vitamin D from the diet, but frankly, except for cod liver oil, there's really no food that contains a whole lot of vitamin D. You guys all take cod liver oil? Is that something you take a lot? Yeah, me neither. So that is not a source. It used to be. So we analyze them because we want to make sure we have enough in the diet, which was mentioned. Nutritional labeling was mentioned. And this one was not mentioned, but it is important. Some of the food processes that we do remove anywhere from a little to almost all of a particular essential nutrient. In this case, we're talking about vitamins. And so we want to know to what degree we've done that. What degree we've done that. Okay. So this is a nutrition facts label. You're all extremely familiar with this. And this is sort of the version that was on packages for a long, long time, showing in this particular case, vitamin A, calcium, vitamin C, and iron. How many of you have experienced vitamin A deficiency? Yeah, me neither. So that's not a real problem. And vitamin C doesn't seem to be a real problem. So consequently, there were some changes suggested to the nutrition facts label, which you're probably all very aware of. And so now we have vitamin D, which was not there before. We still keep calcium and iron, and we've added potassium and dropped vitamin C. We've dropped vitamin C because while scurvy is a problem occasionally under particular circumstances, for example, in refugee camps, they've had outbreaks of scurvy quite regularly. And Victorian prisons in the late 1800s, there were outbreaks of scurvy, but we don't have a lot of that right now. So we focused on things that are more relevant, like vitamin D. All right, so this shows a list of the vitamins, and more or less when they were discovered. Now that doesn't mean that they necessarily knew the exact structure of this compound. They certainly did not know what it did, but they were able to say there's something in here and it's in this fraction of the food and it kind of sort of might be like this, and if you don't have it, bad things happen. And when they did that, that was the year of discovery. Okay, they certainly did not know what vitamin A did in 1909, but they knew it was important. They knew bad things happened if you didn't get enough. And so one by one, you can see the time frame is from like about 1809 to 1941. That was the age of discovery for the vitamins. And since 1941, there have been no additional established vitamins. There was one, there's actually a former professor of mine who thought maybe they had come across a new vitamin, but further analysis indicated that no, that was unfortunately not, or I don't know, unfortunately or fortunately, anyway, it didn't turn out to be the case. So as you know, we commonly break down vitamins into water soluble and fat soluble. Water soluble and fat soluble, everyone knows that, right? But what I want you to understand is that that's only a chemical definition. It refers to the solubility of that organic molecule. So it's either water soluble or fat soluble. It tells you virtually nothing about what the actual compound does. It tells you virtually nothing about the function of those vitamins, whether they're water soluble or fat soluble. Therefore, it is incorrect to say, well, it's a water soluble vitamin, therefore it's involved in these kinds of processes, or it's fat soluble, therefore it does these kinds of things. That's totally wrong. Every vitamin is unique. Every vitamin has its own function, and all the fat soluble vitamins differ from one another. The water soluble vitamins differ from one another. So unfortunately, if you're doing the deep dive into these guys, you have to study each one individually. You can't make these blanket statements. So it creates a lot more work. But that's where the fun is. So this is what they look like. These are the chemical structures. For some reason, Dr. Ishmael left that one off. And so I added it for her. So you can see that the fat soluble ones here have either lots of rings or an aliphatic chain, which then leads to its being hydrophobic in character, and then it's fat soluble. Whereas, in that one too, whereas these guys, if you look at the structure, you can see that they would be much more water soluble. They all have some interesting characteristics. For example, vitamin B12 is the only vitamin that contains a mineral. It has cobalt at the center of it. And so that's a unique characteristic of that. Thiamine over here, one of the first ones to discover, has a sulfur group. Now, before they determined the full structure of it, they were able to figure out that it had a sulfur atom in it. And that is, it had a sulfur and it had amino. And that's where the name came from. Thi for sulfur, amine for the amino group. And that's where thiamine came from those two characteristics. Again, they didn't know the full structure, but they just knew it had sulfur in it and it had nitrogen in it. And they determined it was an amine function. So that's where it all started. And then it's carried on since then. Personally, I really hate the B1, B2, B3. I just call them by their name, and most other people do as well. So I encourage you to do that. So that's what they look like. As you can see, they're extremely varied in their structure, extremely varied, which then makes sense given that their metabolic function is extremely different. Okay, so given that there's this extreme structural difference, the question that Pam would like you to think about, is it possible to analyze all vitamins using one technique? And the hint I give you should help. Of course not. Of course not. Why would you be able to? They're all radically different structures. So no. So there are three general categories that people have created to classify the approaches to analyzing for vitamins. And the first one, bioassays. Now, what a bioassay is that, like its name implies, is that you're using an organism, a live organism, not a microbe. That's a different thing, but like a mammalian system to try and determine the amount of something. Now, in the early days, this is all they had. This is the only test they could do. And so that's what they developed. But they have long since been supplanted with other kinds of assays that don't require a live animal in order to determine the quantity. So it is true that there was a bioassay for vitamin D, but as far as I can tell, it hasn't been used since the 30s. So a long time ago. So microbial assays were in the past frequently used. I actually have a son-in-law that got a degree in microbiology and went to work for a company that was called Covance in Wisconsin. And one of the things they did was they analyzed food for vitamin content. So he spent every day, all day doing microbiological assays for riboflavin, which kind of, after a while, defines the idea of mind-numbing because it's the same thing over and over. Then they discovered he had amazing computer skills and they pulled him out of the lab and now he's in charge of their IT system. So he took a different track, which is good because these are very rarely done anymore. So that leaves this, chemical assays. And so almost entirely, I can't remember the last time when I saw a microbiological assay being done in a research paper. It's been many, many years. So it's essentially, for practical purposes, it's all chemical assays these days of various kinds. So that's the situation there. Now, whenever you're doing these analytical methods, you do have to be careful with some of these vitamins in how you handle the food and particularly the extracts from the food. And you have to know this for each individual vitamin because it's not all the same. pH can be a problem. Light can degrade a couple of these. Oxygen can degrade several of them. High temperature can degrade some of them. So these are all things that are taken into consideration in the analysis of these vitamins. Okay, so lots of different extraction methods, as you would guess, because there's lots of different structures that we're dealing with. And so, for example, with thiamine and riboflavin, you apply high heat. They are relatively stable to that high heat. Acid is required for vitamin C analysis, and the acid of choice is specifically metaphosphoric acid, which stabilizes the vitamin and keeps it from oxidizing and keeps it in its reduced form. So that's an example of acid. And alkali, I'll come back to this one in a big way in a minute. Alkali is necessary to analyze for niacin in certain foods. The fat-soluble vitamins, because they're fat-soluble, you can extract them, or you need to extract them in organic solvents. And the particular organic solvent will vary depending on the fat-soluble vitamin. So it's not the same for even the 4 fat-soluble vitamins. We have to saponify for example, for vitamin A, because it's usually present as the ester, retinol ester. We have to saponify that. And then enzymes are necessary in some cases. Proteases for folic acid to release it from the protein that it's tightly bound to. So we use proteases. And then thiamine is usually present as thiamine diphosphate. So we have to get rid of the phosphate groups. And we do that using a relatively broad specificity phosphatase. So again, you have to understand the vitamin and something about its metabolism in the food in order to know what sort of extraction procedures you need to apply. Now, the one I want to come back to is niacin because it's such a classical case and has tremendous implications for the human food supply. So niacin in plant foods, and particularly for cereals, is present in the form called niacin. Has anybody ever heard of this? Is this something they talk about in another class? Well, I'm glad you're here today then. So in cereals, the niacin is bound up, and it's never been fully characterized, but it's bound up in a agglomeration of peptides and carbohydrates. And this complex is not digestible by mammalian enzymes. So if it is not released from this complex, which we call niacin, niacin is the name for this complex that niacin's bound in, you don't absorb the vitamin, and then you develop a niacin deficiency. So there is a process that was developed by indigenous people, initially in South America, and then it made its way north up in as far as Mexico. And this is called nixtamalization. I assume that's not a word that any of you are familiar with, nixtamalization. So that comes from the Aztec language, nextly, which refers to ashes, and then tamale. You're all familiar with tamales, I assume, like the food, right? And so essentially what they use is lime and ash. The indigenous peoples figured out that the corn, because it was a corn-based culture, that the corn had to be ground in the presence of these materials, that is lime and ash. And if they didn't do that, bad things happened. And so the process of creating this alkali environment for grinding up the corn and then cooking it at the high heat led to the breakdown of the niacin and the release of niacin. So this was developed somewhere, they guess, 12,000 to 15,000 or 1,200 to 1,500 years before the Common Era. And so this was a long time ago. Okay. Shift forward to the early 1900s in the United States. They didn't know about this. And the southern part of the United States became a corn-based culture, and really, really bad things happened. Does anybody know what happened? The name we give to the condition that developed. The name is pellagra. Has anybody ever heard of pellagra? You know, I'm seeing a few heads now. Pellagra is the name we give to a niacin deficiency. And niacin deficiency is characterized by what they call the 3 Ds. Dermatitis, on sun-exposed skin, diarrhea, and dementia. So tens of thousands, maybe 50,000 people died of pellagra, and many, many more ended up institutionalized for the rest of their life because of the dementia. And then there's always the 4th D, which was death. So a lot of people died. So they finally figured out that it was, and there's a whole long and interesting story how they figured it out, and I can't tell you time today because I would need half an hour, but it's a really fascinating story how they figured that out. Because when pellagra was first out, they thought it was a contagious disease, because at that point, all they had was bacterial infections because of the work of Louis Pasteur, you know, and pasteurization. So when all you have is a hammer, everything looks like a nail, right? And the only hammer they had was bacterial infections. So they thought it was that. So some guy figured out that it wasn't, and that it was due to this. So that's the story of niacin, nixtamalization, and release of it. Well, if you're going to analyze the niacin in a cereal, you have to do the same thing. You have to release it. And so you use alkali and heat to do that. Okay. So when you analyze these vitamins, in some cases, more so than others, you have to take certain precautions because you'll lose them in the process of extraction. So we often use antioxidants, and this is particularly important for vitamin C and vitamin E, a little less so for folate, but they use things like beta-mercaptoethanol, glutathione, some other very commonly used antioxidants. Once you extract it, particularly for the fat-soluble vitamins, you want to flush the containers with nitrogen so that they don't oxidize. Chelating agents, why would we use chelating agents like EDTA? What's the purpose of that? You're familiar with EDTA. Is that something you've covered before? Do you know what a chelator is? Is that something you've heard of, a chelator? I'm taking no. You don't really know what?
Binding metals.
It is. It's an organic molecule that binds metals. And chelas is, I think it's Latin or Greek. This stands for jaws. It literally means jaws. So these are like molecular jaws that bind minerals. So why would we want to bind minerals in order to preserve these vitamins?
So if the metals are present, then oxidation happens really fast.
Because they can catalyze oxidation. So that's exactly right. So it is often used in conjunction. They often do both of those, as well as this. These are all related to preventing oxidation. So antioxidants, flushing with nitrogen, using chelating agents, those are all for the same goal of reducing oxidation. We have to control the pH. In the case of vitamin C, we have to keep it low. And that's why the acid of choice, as I said, is the metaphosphoric acid, because it seems to be particularly good for reasons that I don't know, but trust me, it is. It's the best one for keeping the vitamin C stable. Subdued light. In my experimental nutrition laboratory course, which I'll be teaching next semester, we actually extract out vitamin D as well as the form called 25-hydroxy-vitamin D, which is the actual best marker for vitamin D status. And because it's sensitive to light, we literally turn off all the lights in the lab when we do that. And it's for preserving the vitamin D from being broken down. And riboflavin. Riboflavin. You know what a good source of riboflavin is? Anybody? Okay. You're speaking. It's
You want like a grain or like an oat?
yeah, that's not a bad source. But there's a particularly notable source, and it relates to the point here. Particularly notable source. And that notable source would be milk. Milk. So, what do they store milk in the grocery store? What kind of receptacle? Yes.
Pig joints.
Right. Did they always do that? No. And so,
Bags.
what's that?
Talking about bag milk. They have it like Canada. Only Ontario.
Yeah.
That's Canada.
So they used to use, well, first of all, they used to use glass bottles because we didn't really have plastic containers. And then we had a lot of clear plastic. There still are clear plastic jugs of milk in some places. And it turns out the wavelength of light that will oxidize riboflavin goes right through clear plastic. And the wavelength of light that's responsible for that is generated really nicely by fluorescent lighting. And what kind of lighting do they use in grocery stores, right? So some people got used to this oxidized riboflavin flavor, and they thought that's the way milk tastes, but it isn't. And so we, for the most part, now have opaque containers to do that. But that was one of the problems, is this riboflavin, oxidized riboflavin flavor in milk. So, and then low heat for vitamins. I'm sorry? No, it's okay. Go ahead.
I was talking about ice, water with ice, and if I can get milk with its own solids.
I'm not following that.
So like, I don't know, spoiled milk. Show.
Oh, okay. Yeah. Sorry. Okay, so there we go. I'm not going to spend a lot of time on this because, as I said, this is more for historical interest, but examples of bioassays. And I'm just going to talk about this because it's in your textbook, and Pam put it in the slide here. So the vitamin D line test. And in a few words, what they did was they would make rats vitamin D deficient by leaving it out of a diet. So they all got rickets. Rickets is the name of the disease for vitamin D deficiency. And it has nothing good to do with your bones. Okay. And then they would put it back in the diet in varying amounts, and you would get a line. The bone would start calcifying again after it had only poorly calcified, because these are growing rats. These are growing rats. They're laying down a lot of bone, and then you give them a diet that contains some vitamin D, and they can't calcify their bones anymore. And then when you give it back to them, they start doing it, but they have this funny little line between where it was not calcified and where it started calcifying. And that line was measured, but you had to kill the rat. You literally had to take out the bones. You had to cut it and look under a microscope. That's not easy to do. And it's not that specific, as you can imagine. And so we don't do this anymore. But that's what it was. So microbiological tests were commonly done. It was not a rare thing for this. And so what you were looking for was the growth of an organism, microorganism. Now, to do that, you had to use an organism that required that vitamin. That is, an organism that didn't make the vitamin of interest. And so a lot of microorganisms can make many of the vitamins. So you had to find one that didn't. And then you use pure cultures of those. And so then you would have a culture that had a sufficient amount of that vitamin. Let's say, I think she chooses folic acid here as the example. So you would give one culture enough folic acid to support full growth. You give another culture no folic acid, and then you'd give graded amounts of folic acid in the pure form. That's your standard curve. And then you would have other samples where you were just adding the food or whatever it was of interest, water extract of the food or something like that. And then you would just measure the density of microorganisms, usually looking at either absorbance at like 660 nanometers or turbidity. Do you know what turbidity means? Is that a term that you come cloudy, basically how cloudy it got? Yeah, so, and it worked actually. It sounds like pretty hokey in some ways, but it actually worked pretty well. So that was something that was done for many, many years. But as I said, as our, excuse me, as our analytical techniques have improved, those techniques have fallen away. And so it's rarely done anymore. But that was the standard for many years for some vitamins that were difficult to measure analytically. So now, as I said, almost always, we used various chemical methods, and it's frequently involves some sort of chromatography, but not always. And so there's three examples that are done by high performance liquid chromatography, either normal phase or reverse phase. Using either UV detection, for example, or for vitamin E. Vitamin E is nice because it fluoresces, and so that makes it easier to measure because fluorescence is a less common characteristic of molecules than is absorbance. Everything that fluoresces also absorbs, but not everything that absorbs fluoresces. And so if you have a compound that fluoresces, that really makes your job a lot easier. And so use it when you can. So in this case, HPLC, and these days LCMS is also being employed, particularly for vitamin D, is getting very common, LCMS, because there are different forms of this vitamin. And at least in biological systems, it's more common, getting more common to use LCMS. Okay. So Pam wants you to be familiar, be able to name the fat-soluble vitamins. Yes, sir, in the back.
A, B, E, K.
Oh, you're answering the question. Yes, that's correct. Very good. I'll give you a point, but I don't know if Pam does that. So common steps in extracting fat-soluble vitamins. There's really only one. It's very broad. Has to do with, yes, organic solvents. Sometimes you saponify, sometimes you don't, depends on the particular compound. Particular precautions you have to take during sample preparation and why. This is for all the vitamins, not just fat-soluble vitamins. The sort of one I talked about the most was yep, that's true. Probably not the one that I talked about most, but you're absolutely correct. Yes. Preventing oxidation. Yes, that's a very important thing to work on, is to prevent oxidation, because some of them will oxidize very easily. This isn't a vitamin, it's a pre-vitamin, but you're all familiar with beta carotene, right? Yeah. So vitamin A is a little bit sensitive to oxidation. Beta carotene which is going to be in the plants. There's no vitamin A in plants, by the way. There's no vitamin A. It's only beta carotene. So when people say, oh, carrots have a lot of vitamin A, they're a little confused. What they mean is it has pre-vitamin A in the sense that it has a lot of beta carotene and some alpha carotene and those can be converted to vitamin A, okay? So now you know that, so you're way ahead of a lot of other people, okay? Beta carotene is unbelievably sensitive to oxidation. I mean, you just have to kind of look at it hard and it starts to oxidize. So it's really, really hard to work with. Okay, so we haven't even talked about this here. Did she talk about this in some other context? The assay? Okay, well, it's coming in a little bit. So when you want to measure vitamin C in food sources, it's common to use this titration procedure using indophenol acid, indophenol, and this dehydroascorbic acid is the oxidized version of ascorbic acid. Okay, so you have ascorbic acid, it oxidizes, it becomes dehydroascorbic acid. It's still of interest to know how much dehydroascorbic acid there is, because our bodies can convert dehydroascorbic acid back to ascorbic acid. So in fact, the oxidized version of dehydroascorbic acid has vitamin activity. That is, you can feed a guinea pig or us, because we need vitamin C, guinea pigs need vitamin C, a diet containing only dehydroascorbic acid, and they'd be fine, because they can convert it back to ascorbic acid. We have biological systems that do that. Is that clear? Or am I confusing you guys? It's clear? Okay, good. All right. By the way, does she give you a break, or do we just go the whole time, or how does that work? No break?
Just go.
When do we end? 1:40? Okay, the reason I ask is she gave me the wrong time for lecture today. She said 12:30. I was here at 12:30. You guys weren't. And so I was really confused. Anyway, fortunately, I got it figured out. Okay, so you're going to be doing vitamin C analysis in food analysis. And so you're going to be using this method that uses 2,4-dichloroindolphenol, and it's a titration procedure. And so in this particular procedure, you actually oxidize the ascorbic acid to dehydroascorbic acid as part of the assay. And and so when all the ascorbic acid is oxidized to the dehydro form, then the next, because it's clear at that point, in the next drop, it starts to turn pink. So this particular method, as it stands, does not tell you how much dehydroascorbic acid there is. Okay, and in foods, generally, it's not much. In biological systems, it can be a lot. So if you wanted to measure the total vitamin C, so the ascorbic acid and the dehydroascorbic acid, how would you do it? Just broadly, not real specifically, just broadly. So ascorbic acid is the reduced form. Dehydroascorbic acid is the oxidized form. The method we're using measures the reduced form. So what do you do with the oxidized form? You reduce it. Not complicated. Well, to do it's a little complicated, but the concept is simple. You just take your sample and you add a reducing agent to reduce all the dehydroascorbic acid to ascorbic acid. So that's the theory anyway. So as it is set up though, this only measures the reduced form. But in foods, for the most part, that's what you're working with. So it's not an issue. Biological systems, as I said, that's a different situation. And, you know, in your plasma, maybe a third of your vitamin C is actually in the oxidized form, and more if you smoke. So, okay. So that's an example of a chemical method that you'll actually be doing in class. I don't know when you'll be doing. Do you know? You haven't done it yet, right?
We're pretty much done with the lab. So
You're not doing it?
It does not.
Oh, you guys used to do it in class. I know, because my spousal unit was the lab coordinator before Kat Clemmer. So I would hear about this. So I don't know what happened. Maybe they dropped that lab. I don't know. Anyway, what's that?
I traded apple juice today, but it
Wasn't
wasn't like that.
like that? What do you mean like that?
That's
What were you measuring? Acidity?
Yeah.
Okay, okay, acidity. All right. Okay. So much for that. So why she wants to go over this in such detail, I'm not quite sure since you're not doing it in class. But anyway, if you were doing it in class, this would be the background to it. So you have the reduced form of vitamin C. These hydroxyl groups are the site of a reduction in oxidation. And here's 2,4-dichloroindolphenol. And it's oxidized. This is reduced. So this is an oxidation reduction reaction, obviously. And so then you get the dehydro form of ascorbic acid, and then this becomes reduced here. And the reduced form is colorless. So when the color goes away, I think I misspoke myself a little bit ago. It's when the color goes away that you've hit that point of completely titrating the reduced form of the ascorbic acid. Okay? So that's that. And she also wanted to talk about this one. This is the way we do it in the experimental nutrition lab course when we're using plasma as the substance, not like a food source. We use a fluorometric technique. And what we do is we actually oxidize all the ascorbic acid to dehydro. As I said, about 2/3 is ascorbic acid and 1/3 is a dehydro, but we get it all in the dehydro form. And then we add olphenylene diamine, and it goes under a rather complex reaction, and it forms this compound here, which has a long name, but it's just abbreviated as quinoxylin. So that's quinoxylin. It's intensely fluorescent. And so we measure this by a fluorometer. And so, as I said, all the ascorbic acid is oxidized to the dehydro, react with olphenylene diamine, and you get a measure of total ascorbic acid that way. Okay. Well, too bad you're not measuring vitamin C. Okay. Excuse me. So thiamine and riboflavin are two vitamins that are important to measure, particularly in certain foods. And why would that be the case? What's special about these two vitamins in the food supply? Say that again.
It's kind of right identity somewhere, but
Not exactly. The term I'm looking for begins with an F. It's not an obscene word. Begins with an F, ends with a shun. Say that again. Fishing. How do you spell fishing?
No, that's vision.
Fission. Oh yes, fission. Yeah. Okay. It's a process. The term I'm looking for is the procedure where you add something to a food. Fortification, right? Nigel. So to flour, we fortify with certain vitamins and a mineral because of the fact that prior to doing this fortification, people, there was widespread deficiency of these essential nutrients. So what do we fortify flour with? I told you two of them. Niacin, thiamine and riboflavin, right? What else? There's two more things. Iron, that's correct. And the most recent other compound to be fortified only started in 1999. No, actually not calcium. Calcium is fortified in other foods. I'm talking about cereals. You guys are in the food industry. You need to know this.
I work with flour.
Yeah. Say that again. No, it's not zinc. It should be. We should be fortifying with zinc, in my opinion. I'll narrow it down. It's a water soluble vitamin. Pardon me? No, it's not vitamin C, but it's vitamin C is added to other things, you know. D? That, you can't ever say vitamin B in my presence, okay?
Is it folate?
What'd you say?
Folate?
Yes, it is folate. So, once again, to review, thiamine, riboflavin, niacin, folate, and iron are added to white flour to replace that's lost through milling to approximately the level they would be present, with the exception of folate, to the amount they would be present if you had not milled it. Okay, yes, ma'am.
Question about fortification? If that's okay. Or I didn't-
Yeah, no, yeah, go ahead. I'm sorry.
You know, all curious.
Yeah.
So based on prevalence of deficiency, like around the world, how often do they like reevaluate that? Because maybe or fortified also, like what's present on our nutrition label, you know, how they change, the minerals and vitamins that are present on the nutrition label.
Right.
How often do they reevaluate that?
Reevaluate the amount they should be adding or whether they should be adding new ones or taking away. Depends on what you mean by reevaluate. There are people who have promoted adding various essential nutrients, and so therefore vitamins or essential minerals over the years. And like I just mentioned, I would be in favor of zinc. And I think it's unfortunate we don't, but it is talked about a lot. But to get that done, I don't know to describe how difficult it is. I don't have the words to describe how difficult it is. And so, no, they don't do it very often. So there's another, so milk is fortified with something. What is that? A little louder. Vitamin D, right. And so the thing to know about that is it's not required. There's no law that says milk has to be fortified with vitamin D. So virtually all dairies do this out of the goodness of their heart. And I'm not making that up like I do most things, including most of the stuff in this lecture. But if they do add it, they have to put it on the label. And it's at a standard amount. So it's 400 international units per quart is what they do. So, okay, so where was I? I have like 10 more minutes, right? Should be no problem.
2-1.
Quarter to one?
You're good.
Yeah, no, I'll still be okay. I think I'm getting towards the end. So, so this is riboflavin. It's intensely colored. Intensely colored. So what is this? What's that? That is correct. That is a specimen sample. I was going to put a picture of a toilet where that I decided not to do that. But one way to show that you have really good riboflavin nutriture, as the phrase goes, like after you take a vitamin supplement or a multivitamin supplement, is that very quickly your urine will turn very yellow, and that's from the riboflavin, because it is so very, very colored product. So try it at home. It also, as I mentioned, it fluoresces. So what you do is you get your black light, because you all have black lights, right? So get your black light, take a handful of a vitamin mineral supplement, that has riboflavin in it. Wait an hour. Do this at night. Go in, turn the lights off in the bathroom. Void your bladder, and then turn on the black light, and your toilet will glow. So it's a party trick, Say that again. If I had an idea what +2 was, I had answered that, but I don't. What's that? Extra credit? Yeah, sure. Yeah, tell Pam I approved it. Yes, big fun. See, vitamins can be so much fun. Who knew? Who knew? Okay, oh, that's it. That's it. I forgot. I knew I didn't have many slides left. I actually had none. So, so at this point, I think the main points on this particular slide is that for thiamine, as I mentioned, you need to hydrolyze the diphosphate off of it, because that's the way it's present in foods, is the thiamine diphosphate. And so you need to have a phosphatase that can remove that diphosphate group from there. Once you do that, there's also various kinds of chromatographic cleanup. I don't know if you've ever heard of like solid phase extraction columns. Is that something you've used in class? No? Take my lab class, you'll get to use them, but clean it up, and then you oxidize it to thiochrome, the thiamine to thiochrome. And the reason you do that is because thiochrome is also very, very fluorescent. So thiamine itself is not fluorescent, but when you convert it to thiochrome, it is intensely fluorescent, and that makes it easier to measure, as I mentioned. Measuring things that are fluorescent is much easier than measuring things that absorb at a particular wavelength. Now, riboflavin is inherently fluorescent, as I just mentioned, which you can prove to yourself. And so you don't need to oxidize it to do that. So the point is that there's a lot of different methods for analyzing vitamins. It's rare that the same method can be applied exactly to more than one vitamin. The only exception I can think of, I think it's vitamin A and vitamin. It's not even vitamin D. Were sometimes measured in the same chromatographic run. You could extract and analyze those, but that's about the only example I could think of. And so this is why vitamin analysis is such a nightmare to the food industry, because every vitamin has to be measured in its own unique way. And when we talk about minerals next time, you'll find that that's not the case. It's in most ways much easier. Okay, questions about vitamins? No. Yes, sir.
You mentioned that milk doesn't have to be fortified with vitamin D. Does salt have to be fortified with iodine?
No. So do you guys use sea salt? Any of you guys use sea salt? You know how much iodine is in sea salt compared to regular salt? Yeah, there's like no difference. So sea salt is not a good source of iodine. It's a terrible source. And so I would strongly recommend you all use, at least some of the time, iodized salt, because it is a situation where the northern part of the United States where we're living is called the goiter belt. Iodine deficiency leads to the growth of a goiter, which is an overgrowth of your thyroid gland. And we have, and I blame the glaciers for this. They scraped off all the topsoil and put it down in Iowa. And so we have a lot of low iodine. Most of this area is low in iodine. So you should be getting some iodine either from a supplement or from using iodized salt. And it sounds like it was common back in the 40s. It wasn't that long ago that people in this part of the world where we're living had iodine deficiency. And I even had a student in my class this was pre-pandemic, so it was about 5 years ago. She was recovering from a very mild goiter. How can that even happen? But when I quizzed her, no, she never used any kind of salt, and she avoided any kind of food that might contain iodine. No seafood, for example. She got a goiter. So, okay, gang, it's been great. Thanks for showing up today. Look forward to seeing you on Wednesday. We'll talk about minerals.
Thank you.
You're welcome.
Yeah.
The extra credit assignment